Let's start. My name is Roman, and I will be talking with you about dynamic filtering and its application for Presto join optimization. So let's start. This talk will be started. I will start with describing existing join optimization in Presto, which can be useful for you even if you're not using dynamic filtering. Then we'll describe the problem we were trying to solve with dynamic filtering. Then we'll discuss a bit about existing implementations and our proposal. Yeah. And the last slides will describe the performance gains that can be reached using this technique. So let's start. So currently, Presto supports a few optimizations for joins, which happen during the planning phase of the query. The most important ones are join reordering and join distribution type selection. And both of them can be done manually, can be enabled or disabled manually. But the new and the interesting feature is that they can be enabled automatically using the cost-based optimizer, which is a quite new feature in Presto. It was merged, I think, in the last year, in the previous year. And it requires column statistics to do the correct optimizations, which will be described in the next slides. And the statistics can be provided by the connector, which currently is provided by the Hive connector. And if your connector don't provide it, you can use the analyze statement to collect them in runtime. So let's start with the first optimization, the join reordering. So consider the following query where we're doing a join between a large table, the sales table, and the small table, which is the item table. And you should remember that Presto reads the right-hand side table into memory before doing the join. So we would prefer to have the smaller table on the right-hand side and the larger table on the left-hand side. So you can do it manually by flipping the order of tables in the query, but it's a bit tricky. And when your query is large, it becomes more and more tricky to do correctly. And you can, on the other hand, you can enable this optimization by flipping a session parameter. And if your table can tell Presto how large it is, Presto can do it automatically for you. So it's a nice trick. You can use it today. Another trick you can do with if your right-hand side table is very, very small, instead of repartitioning the whole both tables, you can just broadcast it, and this is called broadcast join. It is a type of a distribution type of the join. So instead of repartitioning, you can just broadcast the right-hand side to all join workers, and then the main benefit you get is you scanning the splits of the left-hand side table sequentially without any repartitioning. So you, you don't have the CPU cost and the networking cost, which is happen when you do distributed join. On the other hand, of course, if your right-hand side is too large to fit in one node memory, you need to do the distributed join, and then you can achieve and do joins on much larger tables. So switching between those kind of joins is also done in a session parameter, but the cost-based optimizer can do it depending on how large is the right-hand side, and he can estimate the cost, which is actually computing the cost of the CPU, the networking, and the relevant between the two relevant joins, between this one, and choosing the one which is has the least cost. So now this is currently we can now start to describe the dynamic filtering problem, which is quite similar to the previous one, but now notice that we are using a predicate over the right-hand side table. For example, this query, we're interested in how much in how much sales we have for the most for the items that have the largest price. Okay, for a quite large price. And note that we don't know their IDs. We're doing the join over the IDs, but we don't have the IDs beforehand. We can have them after we scan this table, and we estimate that this join will be very selective because we don't have many expensive items. Okay, so when we finish this scan, we probably have a few item rows coming from here into the join. But then Presto will need to scan the whole left-hand side table. And if it is large, and usually it is very large, it will read the whole of it. And probably most of the rows won't be relevant for the join and will be dropped. So it is very inefficient to do it that way. So what can we do? We can split it into two queries. We can do initially this query, get the item IDs, and then do a query on this table. But it's a manual solution. We would prefer the database to help us, the database engine to help us here. So how can we optimize this use case? So the solution is, of course, in the title, is dynamic filtering, is to enable the database to collect the relevant IDs from the rows it gets from this scan. And then those IDs are used to construct a predicate, which is called the dynamic filter, and which later, after the scan is over, can be pushed down into the scan over this table. When we get this predicate, we use it as we use dynamic predicate pushdown, which our connector supports and improves the performance significantly. We will take a look at the numbers in the end of the slides. But the main benefit is that the scan can be optimized significantly if we don't look for the if we don't do a full scan, but we look for specific IDs. For example, if there are only 2 or 3 items with such a large price, we don't need to scan the whole table and then drop it at the join. We just can pick up the relevant sales rows relevant to those specific items over here. So, of course, most of the rows in this case won't be touched by Presto at all. So our connector will be just picking those and pushing them to Presto. So very few sales rows will come there, and we'll probably have significant CPU and networking savings. So, of course, in order to implement that, the dynamic filter F, which is constructed here, should be quite small. We currently we don't support large dynamic filters, but the main issue is to implement this kind of communication between this part of the scan and computing the dynamic filter, and then pushing it down to this scan. So let's talk a bit about the implementation. So one implementation that was kind of a prior art, suggested by folks from Teradata and implemented by Qubole. It supports both distributed and broadcast joins, but currently it is not part of mainline Presto. It is part of the Qubole distribution, and it's currently being added, in the process of being added to Presto as a pull request. But it does require significant changes in the Presto architecture. It requires modifying the nodes of the query plan and adding new optimizer rules for doing the correct things before executing the query. It requires in order to support distributed join, it requires using the coordinator in order to collect all the relevant filters and to pass them into the application part, into the scan of the left-hand side. And of course, in order to apply them, Qubole and currently the pull request suggests using it for pruning partition during split generation, which can improve the query performance in some cases, and you can find more details over this link. Okay. However, our platform, our Varada platform, we were trying to do something a bit different, which we hope that can be implemented a bit in a bit simpler fashion, and we did it, and we'll describe the details in the next slide. So we've noticed an interesting thing. So when you enable CBO and your left-hand side, and your right-hand side of the join results in a few rows, the CBO can usually convert it to a broadcast join. And then, when you scan the right-hand side table, it results in a few rows. It goes into the hash builder, which is then used to construct the result of the join. We noticed that this hash builder runs when a broadcast join is used. this hash builder and the scan of the sales table run in the same process, the same node. So we don't need to use the coordinator to pass information from this part, from here to here, because they happen to be in the same process, in the same memory space. So passing the information is actually a simple message passing inside the single process. So what we did, we added a new operator, which is just a collector. It just collects the IDs that come from the items, from the item rows. It constructs a dynamic filter as a tuple domain and applies it dynamically into the scan and filter into the scan operator that runs over the sales table, which enables, because we as Varada connector implement this very efficiently, if we have the dynamic filter, improves the scan performance significantly. Okay, so no changes. This solution requires no changes at the planner, no changes in the optimizer, and the coordinator doesn't even know this happens. Okay, and we implemented it as a patch on our Presto of our fork of the Presto repository, and tested it on some interesting for an interesting use case, which will be described here. So in order to test the analysis, we took the TPCDS dataset, and which is one of the largest one. And you can see that the sales table is quite large. It contains 27 billion rows. And we do a similar query. Note that we are doing a filter on the right-hand side table, which we do have a customer ID, but the join is going over the customer SK. Okay, so in order to do the join efficiently, the dynamic filter will need to find the correct customer SK, which is matching to the customer ID given here. Okay, note, so when you run the query, even without any optimization, it results in a very, very few rows. So most of the rows are not relevant to the result of the join. We actually need a very, very small subset of the store sales rows. So it's quite a good match for using dynamic filtering for optimizing this kind of query. So let's take a look at the numbers. So the red column is regular join with CBO enabled running on our cluster. You can see that when we enable dynamic filtering, we process much, much less data, about 8 orders of magnitude less data, because the connector just skips the non-relevant rows. It doesn't need to read it because we compute the dynamic predicate, and this results in much less CPU processing. You can see it's about almost 3 orders of magnitude less CPU time required from the cluster, so the cluster is much, much quieter, and it improves the execution time significantly because we don't need to process all the data that is not relevant to the results of the join. So we can actually, when we saw this kind of results, we were very happy because this kind of method is convinced us that it's very, very efficient to improve the performance of highly selective queries for highly selective joins. So, so to continue, we will continue working on improving and extending the dynamic filtering, and in the next project, we probably will be happy to contribute to aggregation pushdown and the coordinator high availability, the next project that are relevant to the Presto community. And thank you for your attention.